The datasets covers the range of years from 2012 till 2017 for 8th till 12th grade students. We also found three questions which can be solved using the datasets. The first question was, what factors influences being included in above or equal to median value of GPA? The median value which we found was B+. The second question was, what factors influence having a history of gang violence? And the last question was, what factors influence lifetime presence of psychedelic drug use? We decided to do the analysis for solving the problems using R programming. We also used Tableau for visualizations. The system that we constructed for R programming mainly has two files. The first one is cleandatacode.r, which derives final.csv and stores cross-validated thresholds. It also does the factor reduction. The second file is savecsvs.r. This file has the best subset. It also does the class balancing. The file also have ROC curves displaying population model to population data, Monte Carlo model to population data, and Monte Carlo model to Monte Carlo data. The file also checks the VIF for collinearity. It also have the correlation matrix and correlation plots for the datasets. The code we used for combining the datasets is shown above. After combining the datasets, we were left with 182,338 rows and 619 columns. The individual datasets had approximately 30,000 records and more than 550 variables. While browsing through the datasets, we found that there were a lot of NA values. The NA values were often coded as -8 and -9. The dataset had both numerical and categorical values. We mainly focused on behavioral, habitual, and environmental factors for the datasets. This graph shows the percentage values of -1, 0, and 1 after the data cleaning process for the independent variables. The -1 values are the records for values which were less than the median value. The 0 were the missing values. The minimum values of 1 was found for 0.014 for the factor belief of students in better future or worse. The minimum value for 0 was 0.033 for hallucinogens excluding the LSD. For finding the answers for our questions, we decided to do the regression analysis on the dataset. Having said that, our dependent variables are GPA list, the psychedelic drug use, and gang fight columns. This slide shows all the independent variables included in our regression analysis. It also shows the median values for some of the independent variables and also for the GPA. For the data cleaning process, we mainly had three types of conversions. The first one was based on a simple binary 0 or 1 conversions. The second conversion was based on median value. Over here we converted the values which were greater than or equal to median to 1. The third conversion was to split around a positive response. Further, we performed the hypothesis for finding the robust subset. We used the above two formulas for the hypothesis process. We set the null hypothesis for coefficients equal to 0 and alternative hypothesis for coefficients greater than 0. We set to show that the null hypothesis is true by finding all significant terms.
In this slide, we go over oversampling. The way that we handle oversampling in Chimera is that we take a sample. The example that I have here has 25% in the code that is actually in savecsvs.r, but in drawtest.r and drawtrain.r it uses 10%. Anyway, it just grabs the minimum between 10% of the ones and the zeros of a factor, and then it samples 10% of that for the y's from either of those. So it establishes a minimum and it applies the minimum to both sides. It might not be 10%, it's just some value that's derived and applied equally to both sides. This slide gives an example of oversampling that is not symmetrical. It's actually where we were inspired on how to do oversampling. I had no idea how to do this. It didn't occur to me to undersample to oversample. It's exactly what they do. So they just repeatedly undersample to build up this. It's not bootstrapping, because bootstrapping is sampling with replacement on a specific sample. So you could oversample on the specific pass. This doesn't allow you to oversample on any specific pass. Each pass, it has a discrete permutation, and so you just repeat that, and so you construct a reliable mean. We blow up the mean to b.5, and then we derive like a new data frame that is 50% one way or the other for the response. This is a correlation matrix of our data early on before we dealt with NAs to quickly, which was rather intelligent because I didn't have any idea how to deal with NAs early on in our data. So we stored the NAs as zeros, and then we ran a correlation matrix, and this is what came up. And it helped us quickly identify groups of factors. And if you look in the upper right, you can tell that those are like one type of correlated group, and that was substances. And then at V8512 to V8536, starting with satisfied with myself and ending with future life worse, we categorized as psychology. And then you can see the other various ones. We kind of refer to this to help us prune factors as groups, or to include them as groups, or to get a good feel for, like, if we were going to drop one, maybe we should drop another one, because some of them were paired as red and white. You know what? We had to drop two of them, V7501 and V7507, because they had excessive NAs at the time. This was before I figured out how to deal with NAs using paired lists, but for the most part, this shows how we group our factors. So this is one of our early models for tabulation. We used step AIC because it allowed us to feed it a large set of factors, and it would find like best regression algorithm. I think we had holdout analysis at the time. So we were tabulating like successful holdout analysis set of terms, or maybe we weren't. Maybe we were just doing like a single pass. Either way, you know, at the end of the day, it's all just tabulation. And that's what we decided we were going to go with. We were going to find some sort of algorithm that pruned factors. Step AIC was one candidate, and then tabulate the surviving factor. And I think in this case, we didn't use holdout analysis. We just simply tabulated over a training set. And then we found some inferences that texting, sleep, satisfaction with myself, and feeling good to be alive were highly correlated with substance. So this is our slide about data partitioning. It doesn't do it justice. We have a lot of files that deal with data partitioning. But basically, we do indexing, and we only send 2 columns at a time plus a Y to help deal with the issue with NAs dropping too many records. So we only test that many. So that's the whole point, is that we tabulate like small sets of columns. And so that's how the columns are constructed, and then the partitioning works by having a holdout set and a non-holdout set. The non-holdout set is everything that isn't the holdout set. So the holdout set's 10%, the non-holdout set's 90%. But we don't really focus with the non-holdout set. We drill in to a pre-trained set, which is equivalent to 10% of the same size as the holdout set, whatever the math that it is to get to that 10%. 2 partitions, and then we reset those sets 10 times. So we issue 2 10% partitions that are distinct, and then we reset that 10 times over the system. And then we reloop over each set 3 times at 33%. So Monte Carlo resample. So everything's Monte Carlo resample, except it's not an exception, but while we Monte Carlo resample, we still have a holdout set. So we have a training set, we feed data through it, and then it goes to the holdout set, which is a distinct data partition. So we run the same test, same structure. It's just a different set of records, same column. That was the difficult part. It had to be the same column, it had to be the same test. It's just a different like scrambling of the data. An example of our best GLM modified algorithm. So this shows like how our algorithm is different. Generally best GLM will give you like 1 or 2 factors. In this case, it's giving 7. Why? Because we already hand-picked the factors for best GLM using tabulation. So it returns a large number. Normally that's not the case. The point of this is to show you that we skim like the top half based on this column sum tabulation of whether or not that factor was included in the best subset. So there's 8 subsets here, and V7215 was included in 7 of those subsets. So it gets a column sum of 7. So we add all those column sums, and then I pick the top set of column sums that are equal to or greater than the median. So it effectively picks half based on this scoring system. And so it allows me to like pick more than what best GLM normally does, but it always returns something. That's what its purpose is. That's why I went with it versus step AIC. This gives an example of the paired lists as they go through our data.train, and then afterwards they go through data.test. Now data.test is structured the exact same way, has the exact same number of records. Heck, I mean, even it's Monte Carlo class balanced. It's just here in this picture, the holdout is like this last column almost, but in our case, it's a data frame where we run cross-validation as well. Usually in holdout analysis, you use the holdout partition to do like RMSE, and it's like 10% of your training set. But we're not doing that because it's too complex. So we just feed it a set of names, and if those names seem to pass that holdout partition the way that they pass the training partition in the same pair off, then it's tabulated. If it's not, then it's not tabulated. So our goal is to catch like rain, all these like perfect fits. And we know it's not going to happen all the time, but we know like it's going to happen some amount of time, and then we're going to observe, and then skim that off the top. This details model assumptions. We just check VIF because that was the only way that I knew how to test other than using simple collinearity checks, which was rather difficult. But I read that VIF was superior, and UCLA backed VIF for binary logistic regression. So we check it using MCStat VIF at the end, and nothing ever was flagged. But before we prune any factor, so we check it at the Monte Carlo rebalanced data partition. This is like the cream de la cream of our project. So this over here on the right shows like our factor pairs being tested off with a Y, and then like whichever one is lower. Here in the center, just to the left of that little blue graph where it shows like 3 almost triangle, like red, white, and blue. That is the final .csv sorted propensity graph, like the frequencies of how many times the factor was counted in the tabulation. And then to the left of that, you see like the 10th out of 10th tabulation, holdout tabulation, where 3 resample tabulations were tabulated. So then at the end, in the green, it shows like the final one, which is like the 10th out of 10th one, and then how it's saved to the file in the square to the right of that.
Hi, I'm Prerna, and I will be talking about model comparison and conclude with the inferences. The terms coming out of the clean data are not checked for how well they work with each other, and hence are likely to be collinear. To find always terms that will always converge as significant at the population level, we rely on the filtering power of a class balance Monte Carlo constructed data frame to give us our final subset for this potential collinear list. We then compare model parameters derived from the best GLM output from the class balance Monte Carlo partition we created against the population's best fitted model. We then compare ROC and confusion matrix accordingly. Our model has a high sensitivity yet perform worst in the first and third population fitted comparison in overall accuracy. This is because the population fitted model failed to detect any ones whereas ours did. This is because the predicted values of the populated fitted model were all below 0.5. Further analysis in trying various cutoff threshold might actually return some ones or maybe not depending on how the model was trained. Whereas our Monte Carlo based models perform near the accuracy levels they stated they would for the Monte Carlo data frame. The purpose of this is to show how a model does in comparison against population data. When the class is balanced, such as the second model, which is the GPA, our robust model performs nearly as well as the population fitted model. This is actually pretty decent considering that our Monte Carlo simulated model is based on 20,405 records and the population fitted model is based on 48,693 records. When adjusting cutoff threshold for optimal threshold at the population, our model compared the same as the population overfitted model, telling us our model is optimized at 0.5 threshold.
This is the regression equation information on, as well as the population summary information for the stratified resampled data frame that we used for cross-validating the final subset, as well as the population data frame and its parameters. And we give the population model on the bottom, as well as the Monte Carlo model on the top. And they both show that they're significant, and you can compare the coefficient terms. And this is across the board for all three models. This model in particular overfits to the population because it's got a 2% mean, which is interesting because that's what's interesting about a semiotic binary prediction matrix. You have ones and you get the average of a column, and then the mean, that's the percentage of. This slide shows what factors actually made the cutoff threshold. We have a cutoff threshold set at 0.35. So the factors that made the cutoff threshold was feels good to be alive, life seems meaningless, how often, 7 hours sleep, satisfied with myself. And the ones that were highlighted in dark blue, life seems meaningless and satisfied with myself, would be positive responses that made it past the threshold, but also survived the CV cross-validated algorithm. This shows the predictor effect plots as well as the correlation plots. It shows how the response term is negatively or positively correlated with a dependent term. And it also has like a graph, an XY graph, as well as ROC chart and fusion matrices with error ratings. And it shows you how much a change in response. Say if respondent says that yes, their life is meaningless, then they have a plus 20% chance. Population-wise to use psychedelic drug use. And our model has a 35% error rate. And then the model applied to the population had a 38% chance error rate. So probably, not probably, using statistics, laws of proportion, you can derive the standard deviation of that error and stick with that for the model strength. And you can say that they say yes to that question, life is meaningless, then there's a 20% chance increase. You can derive a prediction interval based on proportions. And the same goes for if they answer yes, that they're satisfied with themselves, then the chance goes down 18%. These give the three regression equations for the three questions that we set out. V7118 is related to psychedelic drug use, V7221 is related to GPA, and V8517 is related to gang violence. The only one that is not biased is V7221 to begin with. However, we still class balance all of them. This is the main takeaway. The way that we build our models, we start small. and then we build up. We start from a null model, and then we add factors. So it doesn't make a lot of sense to try to do a McFadden R squared, because we don't start with like a really large model. Although you can start with a null model. However, we just derive an error rate. This gives us the error rate, and we trust it. We see it apply to the population, and it stays around there. Although the error rate seems to stay around the same around all three models. However, what's more important is the factors of influence. And so that change represents holding else at 50% if you assume that you can either go up or down. This represents a percent change if you have a 1 unit presence in that factor, so that independent factor. So if you have 8502, life is meaningless, if you respond to that as yes, then your chance goes up 20% for psychedelic drug use. On a population level, however, the prediction interval could be derived for that. The prediction interval could be derived for all of these, considering that they're all proportional.